All right, so looking further at similarity and the criteria that's involved with angle-angle, side-side-side, and side-angle-side, we're looking at a couple of basic proofs with this in this section. So in exercise 1, the diagram is showing AE and BD intersecting at point C, and it's also telling us as a given that AB is parallel to DE, so we can prove that the two triangles are similar. So what we want to think about first before we even start this proof is which of our three codes we might be going for. So when I see parallel lines, I'm typically thinking about equal angles. That's usually what parallel lines lead me to. And I also don't see any information in this problem whatsoever about side lengths to be able to prove proportionality. So the code that we need to go after here is AA. And looking at this diagram, we have vertical angles at angles 3 and 4. And we also have alternate interior angles because of the parallel lines. So after we write our given, we can write either the vertical angle pair or the alternate interior pair. And you don't have to write quite as long an explanation for step 2 as what's written here. You can just write alternate interior, that's sufficient. And for the last step, when we say that the two triangles are similar, we just have to make sure that we name them correctly. So we can take that name right out of the problem, or we can just make sure that our angles match up. We know that A and E are in the same spot, that C and C have to be in the same spot, and therefore B and D as well. So at the end, you don't have to write similarity theorem, just AA will work, and you have your proof. So there's only 4 steps to this. So just like with congruence proofs, we want to look at the diagram, see what we know, and make a plan for which code to go for, and then go from there. All right, so it's very often the case that when we're trying to prove two triangles are similar, we need to establish angles being equal. So as we look at this proof in example 2, we have MN and MP are congruent. So that is on the sides here. So that tells me right away we have an isosceles triangle. And RS, T, and W all lie on the sides of that triangle and making perpendiculars. And what we're trying to prove is that NTR is similar to PWS. So locating those triangles, NTR is over here, PWS is over here. And this is being done in a paragraph format here, but you could do a 2-column if you wanted to. Basically what we have for given information is the equal sides and the perpendicular sides. So if I'm writing those on line 1, my line 2 could either be that the angles RTN and SWP are right angles and therefore congruent, or I could say that angle N and P are congruent because of the isosceles triangle base angles. Either one of those would be a reasonable second step, and then the other would be the third. That's enough for similarity right there. To have two equal angle pairs, the sides don't matter. We'll have proportionality and we'll have similar triangles. So the paragraph here explains all of that. You can write it out that way, or you can go with 2 columns, whatever you prefer. Part B is now putting numbers into the situation. So if RT is 12 and PW is 3, and SW is the same as NT, solve for the length of SW. So what's happening here is we've got a proportion. We're saying that NT over PW, which is left over right, is equal to RT over SW, which is also left triangle over right triangle. We've got base, the 2 bases in the first fraction, the 2 altitudes in the second fraction, so that all matches up perfectly. And what the problem tells us is that NT and SW are the same, so we don't know either one. We'll just put x's in those spots. We have 3 and 12 for the other ones that were given to us, and so we can say that x squared equals 36 by a cross product. And we just do a square root and we get x equals 6. So in this case, we did not have enough information for a scale factor, but because the 2 sides were equal, we could put them into a proportion and solve it that way. All right, on the next page, there are some times when other reasoning besides angle-angle will be in a proof, but we should always consider whether we can get 2 angle pairs, because that is typically going to be the easiest way. In diagram shown, midpoints of AE and AD have been drawn as C and B. And so if we sketch those 2 triangles separately, the small one is here and the large one is here. CB would have been in the middle. And what angle must be congruent between the 2 triangles? Well, they both contain angle A. So this is a situation where we have 2 triangles nested into each other. So it's kind of like when 2 triangles share a side in congruence proofs. A lot of times in similarity proofs, you're going to find 2 triangles that share the same angle. So if we're trying to justify that, we would say reflexive, just like we did with shared sides. So that because angle A is a shared angle, we have one angle pair right there. So maybe that's going to be used in angle-angle, maybe it's going to be used in SAS. But in this one, we want SAS because what's happening here is C and B are both midpoints. So that tells me that the distance from A to E is double the distance from A to C, and the distance from A to D is double the distance from A to B. So that gives us proportionality. We can say that AE over AC is the same scale factor as AD over AB. They both equal 2. That proportionality surrounding angle A is what side angle side means. It's two proportional sides that have the same scale factor surrounding an equal angle pair. So SAS works. Why must angle EDA be congruent to CBA? EDA is here, CBA is here. Those two angles are corresponding to each other, and they are corresponding in the similar triangles, that is. And so any two corresponding angles in similar triangles are going to be congruent as well. So it's not CPCTC because it's not corresponding parts of congruent triangles. It's just that similar triangles lead to equal angles. Okay, and exercise 4. In the diagram below, parallelogram ABCD, which is going around here, has point P on the onside CD down here, and AP has been extended, and BC has been extended. So we want an argument for why triangle MCP, which is this little one, is similar to both ADP and MBA. Now this looks like a perfect candidate for angle-angle because parallelograms have equal angles all around. So, well, not all four, but equal pairs of angles all around. So let's see if we can use that. So I've got AB parallel to DC and AD parallel to BC. That's just definition of a parallelogram. So looking at some transversals here, I'm noticing that AM is a transversal for this extended ray BC. So angle 2 must be the same as angle 1. I also know that angle 3 is the same as angle 4 because they're vertical angles. So that is enough information right there to say that ADP and CPM are similar. ADP and MCP. I want to make sure I'm naming those the right way. ADP and MCP. So angle-angle for those two. And then if I want to compare the others, because AB and DC are parallel, I can say that angle 5 and 4 are congruent because they're corresponding angles. And both triangles have angle M. Triangle ABM and triangle PCM both contain this angle 1. And so there's another angle-angle argument for that one. So a lot of times when we see parallel lines, we're going to try to get angle-angle. Occasionally we'll have an SAS, but we need to have information about the scale factors in order to use SAS, or SSS, that is.